Okay, hello, it's me again. I am going to try to keep this under 1 hour. What is the agenda? Well, this is the agenda. We are going to look at measures. I'm starting from your left hand side. Measures of variation, R squared. We'll look at how to calculate R squared, an example, a high R squared, a low R squared, a good R squared, what those mean. We'll look at some non-linearities. So Spencer, here is to your question. And I will take a moment to go over what exactly it is that we are doing. And this goes back into sampling distribution, just like we discussed in class. So a bit of this has been covered in class, which is good. Then we'll jump into the 4 assumptions that we make to establish unbiasedness of an estimator. Now, if those 4 and a 5th, known as homoscedasticity, I will get into that, I promise. If those 4, now 5, hold, then we can write the variance of our beta as sigma squared as this. Sigma squared of the sum of squares total in X. And we have to estimate that sigma squared. That sigma squared is known, when we estimate it, is known as estimating error of the variance. And this is how we estimate it. So again, Spencer, you were right onto something in class last time. Then we look at some terms, homoscedasticity and heteroscedasticity, and we'll call it done. So here are the slides for chapter 2. Let's see if okay, everything looks good. All right, so goodness of fit. We are inching towards R squared. R squared is the percent of variation in the regression model that has been explained by our regression of Y on X. How do we calculate that? Well, we use these measures of variation to calculate that. We will take the explained sum of squares and divide that by the total sum of squares. So if our explained sum of squares is larger, our R squared, which is measuring the variation that is explained in the model, that will get bigger. And here we go. Here is how to measure R squared. R squared is measured as the explained sum of squares divided by the total sum of squares, or 1 minus the residual sum of squares over the total sum of squares. Again, R squared is measuring the percent of variation that is explained by the regression model. Here's an example. We have CEO salary and return on equity. So our return on equity is our explanatory variable, and salary is our response variable. After running this through the software, we get an R squared that looks like so. Here the R squared is 1.332%. In this second regression, where we are running the regression Y on X, our Y is our vote A and our X is our share A. R squared here is much larger, 85.6%. Here is where I tell you to never chase high R squared. What exactly is R squared saying? Well, for one, the R squared, a high R squared, does not mean that the regression has a causal interpretation. It just means that vote A, in this case, vote A and share A are highly correlated. That's all it says. What is a good R squared? We went a bit into this in class last time. A good R squared depends on your field of study, and it depends on the context. In finance, a good R squared or a strong R squared is 0.8 to 0.9, while 0.3 or 0.4 or 0.5 are considered weak. But in some fields, 0.3 to 0.5 are considered strong. You see? So you do not chase a high R squared. Now, by the way, as we get into multiple linear regression, the more variables you add, the higher the R squared becomes. Yes, R squared never falls. That's one interesting thing. So, all right, visually, what is a big R squared and what is a small R squared? Visually, a big R squared will be your panel A. If you notice, the fitted line is steeper and the data points cluster more closely around the line. We went over this in class. And a small R squared will be panel B, right here. The fitted line will look flatter relatively, and the data points will not cluster closely around the line anymore. Again, the R squared never falls. Even if we add irrelevant variables, the R squared doesn't fall, it keeps increasing. So this tells you that you can't just look at the R squared and believe that your variables are relevant. You have to spend some time, like we saw in chapter 1, in the economic model phase, where you establish relevance of the variables that you are adding into the model. Right, so this is more of a black box. It's not that smart to know that the variables are relevant or not, but we can get a little close. We can use the adjusted R squared, which adjusts for adding additional variables. Now, the context of this is a bit more complicated, and I'll get into that in chapter 3 when we work on multiple linear regression. For now, just know that the added variable, if it is irrelevant, the adjusted R squared will fall. Okay, let's go back to the agenda. Where am I? I just finished measures of variation, and I am currently working on nonlinearities. Now, Spencer did ask a question about this last time, so here you go, Spencer. We can incorporate nonlinearities into our model. For example, we can have the log level form, where we log wage and we don't do anything to the education variable. When we use the log level form, this changes the interpretation that we have for our variables or for our slopes. We are interpreting the slopes. Right? Okay, so what did we have before? I'm going to go all the way back. Yes. Before we had, I'm going to use a different color now. Let's try red. Let's try blue because I already have red on here. How do I interpret this? How do I interpret this? For every unit increase in ROE, salary increases by, since salary is in thousands, this is $18,501 on average, right? We know this, or we call this level. So level, and we will interpret that slope as for every unit increase, in ROE, salary increases, because it's a plus 18.501, right? Salary increases by, well, 18,501 on average. That's a level interpretation. Okay, cool. Now, for a log level interpretation, just because we have that log on the y variable, for a log level interpretation, we will take our beta 1 hat, whatever it is that we end up calculating in our regression output. We will take that beta 1 and multiply it by 100%. So we'll say that for every unit increase in education, wages increases by beta 1 times 100%. So this is known as the semi-log form. And here's an example. Okay, so here, how do I interpret this 0.083? Well, for every unit increase, or for every additional year of schooling, wages increase by, what is 0.083 times 100? That's 8.3%. Yeah. For every additional year of schooling, wages increase by 8.3% on average, right? On average. And how that graph is drawn, it's quadratic, or it's exponential, right? So this is the growth rate of wages per year of education. It increases by 8.3% every year. Can we have the log form? Yes, we can. When we have the log form, beta 1 becomes elasticity. And those of you taking my micro class, you know what elasticity is. Elasticity is the ratio of percentage changes. Now, for those of you who need a bit of elasticity, for those of you who need me to remind you, elasticity is calculate price elasticity of demand, actually. Price elasticity of demand is calculated as percentage change in quantity demanded over percentage change in price. But the idea here is it's a ratio of percentage changes, right? So regardless of what our y and our x are, we are looking at an elasticity. So for every percentage change in sales, right, this is how we'll interpret beta 1. For every percentage change in sales, salary changes by some percentage. And here's the example, right? For every 1% change in sales, salary changes by 0.257%. Now, for every 10% change in sales, increase in sales, right, salary will change by 2.57%. Increase in salary. Do you see what I just did there? Pause and take another look. For every 1% change in sales, salary changes by 0.257% on average. Now, for every 10% change in sales, salary changes by or increases by 2.57%. Again, we will run into this again in chapter 3. Here is a summary of the various functional forms that our equations can take: the level form, the log level form, the log level form, the level log form, and the log form. The log form again is elasticity, while this third one is semi-elasticity. Okay, I just worked on nonlinearities. It's weird. I'm not getting any questions today, right? Yeah. What are we doing? We start with an unknown population model. And I do remember getting a question in class. What if we had the entire population? Well, like we said in class, then we are done. Then our beta 0 and our beta 1 are the true. But we'll still have errors to deal with, right? Because some of the variables could have been measured wrong, or we would be missing some variables, right? So we'll still have the error term. Okay, well, we have this unknown population model, and again, it's difficult to get the whole population. So we settle for a sample randomly picked from the population, with a key assumption that there is some zero conditional mean. We can rewrite that key assumption and its implication. We can rewrite it as this, right? And we can rewrite it as this. Now, I did show you some math for why that is true, why these two exist. Okay. Now we go to the population and take one random sample. We take one random sample, we minimize the sum of squared residuals, and in the process we calculate beta 0 hat and beta 1 hat. After that, we throw that one sample back into the population and then reach for another random sample. We do that multiple times and collect thousands of beta 1s or beta 1 hats. We put the beta 1 hats that we have collected into a histogram and we look at where they center around. Where they center is probably the true beta. So again, we are interested in what that random sample will be on average and how large or how wide their variability will be as we repeatedly sample or as we repeatedly randomly collect samples from the population. So we are interested in seeing a distribution of beta 1 hats. Yes. Why? Well, why do we care about distributions and not just the one value? If we are interested in our consumption of electricity or utilities, just looking at one day's value is not enough. So in the winter time, we'll have a different value than in the summertime on average, right? So we take a look at the whole year per se, and we come up with an average over the summer months, over the winter months, etc. So why do we care about distributions? If you're looking at the distribution of your daily consumption of electricity and maybe the bills are too high, you may be interested in reducing electricity on the days that you use too much. So during the summer times, yes. Now, why do I say even camels know this? I don't mean that. I don't mean that literally, but there is a website called Camel, where you can see price distributions of products sold on Amazon, so that you know when to buy, right? When you know the distribution, you can tell when to buy. In case you don't need the product right now. If you need the product right now, you just have to buy it right now. All right. So our beta 1 hat is written this way. The covariance of x and y divided by the variance of x. And our beta 0 hat is written this way, where you have y bar minus beta 1 hat times x bar. So we are interested in what our estimators will estimate on average and how large their variability will be in repeated sampling. We are interested in this. The fact that we don't have access to the entire population data makes it so that we are interested in what they will be on average if we were to randomly, repeatedly sample from the population data or from the population set. Okay, so where are we now in the agenda? We just passed sampling distribution, and we are headed to the 4 assumptions of unbiasedness. These are also the standard assumptions for the linear regression model, and there are more than 4, but we will get to each one. So here are the first 4. The first 4 go like this. We have a linear regression model that is linear in parameters with an additive error, such that we can write our econometric model like so. Y equals beta 0 plus beta 1 hat x plus u. The second assumption is that we have random sampling. Now, yeah, of course, how do you check if you have random sampling? For the scope of this class, we are going to assume we have random sampling, but in the future, when you're dealing with your own data set, you have to check and justify that there was random sampling. If there was no random sampling, that will be reflected in your econometric model, in the econometric method that you use to analyze your econometric model. Now, how do you check for linearity in parameters with an additive error for this econometric model? The way we check is by using a residual plot, and we'll jump into that in chapter 3. The idea here is, in your residual plot, you are not looking to see, or we don't want to see any curves or any curvature. What is random sampling? Random sampling means that each data point is equally likely to be picked, right? So we are not going out there looking for particular sets of data to put into our model, but each one has the equal likelihood of being selected. We did already talk about residuals, so I'm going to move on. I'm going to move on. The third assumption. This is probably one of the most important assumptions here. The third assumption is sample variation in the explanatory variable. Here is how we write beta 1 hat. Look at the denominator. We don't want that to be 0. If it's 0, then, well, our beta 1 hat will be equal to 0 times sum of yi minus y bar over 0. And this is undefined. It will make it difficult if the denominator is 0. And how would the denominator be 0? If each, let's say this is our data set, right? For x, well, this is y, and then this is x. And let's say our x bar, right, the mean of x is 12. And each data point under x is also 12. That's how our denominator is 0. If each value of x is equal to its mean or super close to the mean, then we'll have to divide by 0 or something super close to 0. That's not good. Or that makes our beta 1 biased. So just like the figure on our right hand side here, we don't want this. We don't want this. What do we want? We want to have, so if it's an upward sloping relationship between y and x, then we want some variation in x, or we want enough variation in x so that we can identify beta 1 hat. We want enough variation in x. Now, here is where you may ask me, how much variation? Enough variation, I'll keep saying this, enough variation in x. What does that mean? More follows in chapter 3. But we want to have enough variation such that if we were to visually inspect the scatter plot with y on the y-axis and x on the x-axis, we will have something like this. So if we are unable to, for example, if we are unable to identify our beta 1 hat, do you notice how it will be very difficult to also estimate beta 0 hat? Yeah. So not having enough variation in our explanatory variable x makes our life very difficult. So if, for example, you do not have enough variation in your explanatory variable x, what do? You have to get a larger sample size. So right here, my table, I have only 4 data points, and each one is 12. You can't just say, I'm just going to use, no, please get a larger data set. And as you get a larger data set and each one is 12, then please just find a different variable, okay? And then the fourth assumption, 0 conditional mean. What we are saying here is the backdoor path is closed. Ideally, the backdoor path is closed. That the value of the explanatory variable should contain no information about the mean of the unobserved factors in the error term. Unbiasedness of the OLS. Unbiasedness of the OLS is summarized here. Now, the interpretation of unbiasedness has everything to do with our sampling distribution. That given a sample, our estimates will differ considerably from the true value. So if I take one sample out of the population and calculate beta 0 hat and beta 1 hat, and I take another sample from the population and calculate another set of beta 0 and beta 1 hat, they will be different from one another and from each other, and they will be different from the true value. But then on average, the estimate on average should center the true value. So with repeated sampling, right? So the interpretation of unbiasedness is coming from the fact that we are doing repeated random sampling and looking at the sampling distribution, looking at the average of that sampling distribution and the variance and the variance of that sampling distribution. So the center of the histogram of the beta 1s or the beta 1 hats and the width of the distribution of the beta 1 hats. Now cast your mind to the supplemental slides I showed you last time with the code and the betas that I calculated and put in various histogram bins. By the way, these are also available on the slides, so you could go and look at it right now. Yeah, we are not gonna stop here. We are gonna look at this next bit, and we're almost done. Right, so I just talked about the assumptions of unbiasedness, and we're looking at the fifth assumption now. The fifth assumption is homoscedasticity. This one says that the variance of U conditional on X is some constant value. So sigma squared is a constant value. What does this mean? Homoscedasticity. Well, here is a graph of homoscedasticity. And I can draw a better one. We have 8 years of education, 12 years of education, 16 years of education, and we have our fitted line. If you take the lower levels of education, and if you take the higher levels of education, the variance is the same. That's homoscedasticity. So let me fill in the middle part. Okay. Let's call this education and let's call this wages. So this is 8th grade and below, between 8th grade and 12th grade, and then, 8th grade and below, between 8 and 12 years of education, and 12 and 16 years of education and beyond, right? To display homoscedasticity, we are saying that if you take this slice of the data and that slice of the data, the variability is almost the same. Now, this really is the variability some constant. The variability of the unobserved influences does not depend on the value of the explanatory variable. In reality, though, when you have education, and you have wages, you will realize that at the lower levels of education, wages are sort of uniformed. But then, at higher levels of education, there is small variation. There is small variation in the wages, such that there is this fanning out of the data points. Why? Well, you want to think about the unobserved determinants of wages. For lower levels of education, they are more likely the same, probably earning minimum wage, and the opportunities are low and few. But at higher levels of education, there is more flexibility and there are more opportunities. And so there's a wider range of opportunities than at the lower levels of education. Such that as education increases, those opportunities change with the level of education one has. Such that heteroskedasticity is characterized as the variance of U conditional on X to be equal to sigma squared times some function of X. Homoskedasticity is not characterized this way. Heteroskedasticity. Homoskedasticity, on the other hand, is where the variance of U conditional on X is just some constant value. Heteroskedasticity says that the variance of U conditional on X is, well, the constant value times some function of X, meaning variation will change as education changes. So at lower levels, we will see less opportunity and the majority earning similar wages. At higher levels, we will see more opportunity and more people earning a wide variety of wages. or sometimes even opting out of working. There is more there is more in your textbook, so please take a look. When we meet again, I'll do more with you, and I also have a class assignment over this so that it sticks better. Okay, I'm almost done. So with these 5 assumptions, we can write the variance of beta 1 hat this way, whereby we calculate sigma squared 1 over, in this case it's n minus 2, n minus 2 because we calculated beta 0 hat and beta 1 hat. Right, this is what I just wrote down. Well, actually, this is what I just wrote down. So the variance of beta 1 hat is higher if sigma hat squared is higher, or if the sum of squares total is smaller. So the less variation you have in your explanatory variable, or the less variation you have in your x variable, the larger your variance of beta 1 hat. I'm going to say that again. The smaller your sum of squared total, right, this one, meaning the smaller the variation in your explanatory variables, where they are all sort of close to 12 or equal to 12, where 12 is their mean, the larger the variance of your beta 1 hat. And the larger your residual squared, the larger sigma squared, and so the larger your variance. We will do more on this when we meet in class next time. Let's see. Now, by the way, why do we take standard? Why do we calculate standard error or standard errors? Variance squares the units, and so to go back to our original units, we take the standard error. Right, so that's why we have the standard error here. The standard error is just the square root of the variance calculations we saw earlier, the square root of that, and that just takes us back to original units, right? But what the standard error does is it measures how precisely the regression coefficients have been estimated. Okay. There's a cool rule out there that says that if you have a bell-shaped distribution, then it's the 68, 95, 99.7 rule, all of this in percentages, of course. If you have a bell-shaped curve or a bell-shaped distribution, then 68% of your data will be within 1 standard deviation, and 95% will be within 2 standard deviation, and 99.7% will be within 3 standard deviations. So this works for just the bell-shaped or the normal distribution. That's just a random fact from years ago when I took this at the super basic level with the statisticians. Anyway, I will call it done. Thank you for a good class. I had fun by myself. No questions. Please ask me your questions when we meet again. Okay, have a good Monday and get all your work done. I'm going to see you later. Dr. T.